This is Module 5. In this module, I will give you 4 key formulas for finding derivatives. Then, the rest of the lesson is dedicated to a number of examples demonstrating the use of them. Let's jump right in. Differentiation rules. Now I will present each of these rules using f of x. However, keep in mind that we often use other variables and other function names. The first rule is the constant rule. Now if f of x equals k, where k equals a constant, then f prime of x equals 0. This is pretty easy to see. The graph of a constant function is a horizontal line, so the slope of the tangent line is always 0. The second rule is the linear function rule. If f of x equals k times x, then f prime of x equals k. The next rule is the linearization rule, which states that the derivative of a times f of x plus b times g of x, where a and b are constants and f and g are functions, is equal to a times f prime of x plus b times g prime of x. Note here that the derivative of a constant all by itself is 0, but if that constant is multiplied by a function, it just comes along for the ride. The last rule is the power rule, which states that if f of x equals x to the nth power, then f prime of x is equal to n times x to the n minus 1. Let's get to the examples. In this first example, we're trying to find the derivative of f of x equals the square root of 7. Now, the square root of 7 is a constant. And so using the constant rule here, we can see that this is a pretty straightforward one. We get f prime of x is equal to 0. In part B, we have f of x equals negative 5x plus 9. Now the linearization rule tells us that when we have multiple terms, we just address them one at a time. And in the first term, we have negative 5 times x. And using the linear function rule, we know the derivative here would be just negative 5. And 9 is just a constant. And so what we have here is we have f prime of x equals negative 5. That's the derivative from the first term. And from the second term, we get 0. In this example, we want to find the derivative of h of x equals x to the 7th minus 3 times x to the negative 4th. Well, now we're going to use the power rule here. And in this first term, we have x to the 7th. And so I think we can see here that h prime of x is going to be, let's see, the 7 comes out in front, and we subtract 1 from the exponent, which gives us 6. So we have 7x to the 6th for the first term. Okay, over here, now we have a negative 3 out here times a function. And the linearization rule tells us, let's just keep that negative 3. It just comes along for the ride. So we've got the negative 3, and now we're going to take the derivative of the function part. Well, here I've got x raised to the nth power again. And so we know that we're going to get negative 4 that comes out in front, and subtract the exponent by 1. So negative 4 minus 1 gives me a negative 5. And if we clean this up a little bit, it looks like we have 7x to the 6th. These two negatives will make it a positive, plus 12x to the negative 5th. Note here in this problem that when we dropped this negative 3 down, and we multiplied by the negative 4 when we took the derivative, we ended up with a positive 12. Now we could just do that all in one step. The negative 3 that's already there, and we're bringing the negative 4 down, just multiply them. Let's take that approach here in the second problem. I've got a of t equals 10 t to the negative 2 minus 10t squared plus 3t. And I want to take the derivative. So here I have a 10 that's already out here, and I know I'm going to bring a negative 2 out in front when I take the derivative, so that's going to give me a negative 20. And when we subtract 1 from the exponent, we get negative 3. We have negative 20t to the negative 3 for the first term. Over here I have a negative 10 out front, and I'm going to bring this 2 down, so that's going to give me a negative 20. And when we subtract the exponent by 1 here, we get t. This is a linear function, 3 times t, so the derivative there will just be 3, and we found our derivative. In this example, we want to find the derivative of g of x equals 2 over x to the fourth. Well, now we see here that we have 2 over x to the fourth. We're going to have to use a little bit of algebra here to rewrite this function. I know that when I have 2 over x to the fourth, this is the same thing as 2 times x to the negative fourth. Now, I'm not doing any derivatives here. All I'm doing at this point is just rewriting the function using algebra rules. Now I'm ready to take the derivative. So g prime of x is equal to, let's see, the negative 4 comes out in front, multiply it by the 2 that's already out there, it gives me a negative 8. Subtract 1 from the exponent, so it looks like I have negative 8x to the negative fifth. Now this is perfectly fine as an answer. It's the derivative. But sometimes we will want the derivative to be in the same format as the original problem. So I could write this as negative 8 over x to the fifth, which is very similar to the format of the original problem. In part B, we have f of t equals the cube root of t squared. So we'll take a similar approach here. I'm going to start by rewriting this as t to the 2/3 power. Now again, I haven't done any derivatives here. All I've done is rewrite this using algebra rules. But now it's in the form where I can use the power rule directly. We have f prime of t equals 2/3 t. Now I need to subtract this exponent by 1. Let me just write this out. 2/3 minus 1. Now we know that this is going to be 2/3, and t to the 2/3 minus 1, well, that will just be t to the negative 1/3. And again, here we have the derivative. However, we might be able to simplify this a little bit more. If I take the negative exponent downstairs, that gives me 2 over 3t to the 1/3. Or I might write that as 2 over 3 times the cube root of t. In this example, we have u of x equals the fourth root of x plus 1 over x squared minus 7x cubed plus 12x. And we want to find u prime of 4. Well, I'm going to start off by rewriting the function here. I'm going to write this as x to the 1/4 plus x to the negative 2 minus 7x cubed plus 12x. Now remember, we haven't done any calculus yet. All we've done is rewrite the function. But now I'm ready to do the derivative. We find that u prime of x is equal to, we use the power rule here, so we get 1/4 x, and this will be 1/4 minus 1, which is a negative 3/4. Here the negative 2 comes out in front, so I get negative 2x and subtract the exponent by 1. For 7x cubed, we're going to get 21x squared. Here we have a linear function, 12 times x, and so the derivative there will just be 12. Now I'm not going to bother with doing any kind of simplification here, because what I'm trying to find here is u prime of 4. So I'm just going to plug 4 directly into the derivative. And if I throw this in the calculator, it looks like what I get is negative 323.94. A city uses a network of sensors to monitor for potential security threats, like abnormal power outages or traffic patterns. The effectiveness of the network is related to the number of sensors deployed, S. The effectiveness is given by E of S equals 3/2 times s to the 2/3 plus 6s minus 1 over s squared. We want to find the rate of change in effectiveness at s equals 1728. Well, we know the rate of change is given by the derivative. So we need to find the derivative of E of s. I'm going to start by rewriting E of s. So we have E of s is equal to 3/2 times s to the 2/3 plus 6s. So those two terms are the same as they are in the original function. but this last term, I'll write that as s to the negative 2. Now note here I haven't done any calculus. I've just rewritten the function. Now I'm ready to take the derivative. So we get e prime of s equals, now here I've got 3/2 times s to the 2/3. When I bring this 2/3 out in front, it's going to cancel with the 3/2. So that's just going to give me s. We need to subtract the exponent by 1, so I get a negative 1/3. Here I have 6 times s, which just gives me a derivative of 6. And for the last term, I have a negative 2 that will come out in front. There's already a negative out there, so that's going to give me a positive 2s, and I subtract the exponent by 1 to give me negative 3. So the derivative is s to the negative 1/3 plus 6 plus 2 times s to the negative 3. Well, now we need to find e prime of 1728 to find the rate of change of effectiveness at that value. Well, at this point, I'm just going to plug it into the calculator, and it looks like this is approximately equal to 6.083. In a company, artificial intelligence assigns a file vulnerability score based on the number of unrecognized lines of code, x, present. The score is modeled by v of x equals 2 times x squared minus 80x plus 980. For how many lines of code is the rate of change equal to 0? Well, we know the rate of change here is given by the derivative, so let's start by finding the derivative. We have v prime of x equals, looks like here we will get 4x, here we will get negative 80, and we'll get 0 for the last term. So we want to know when is the derivative equal to 0. So I'm just going to set this equal to 0. We have 4x minus 80 equals 0, which implies that 4x is equal to 80. And if we divide both sides by 4, we get x is equal to 20. So when we have 20 lines of code, the rate of change is equal to 0. We can verify this by looking at the graph. We see that when x equals 20, the tangent line is horizontal, which has a slope of 0. A biometric system verifies users based on the quality of their fingerprints. The success rate of the system is modeled by f of x equals 0.9x squared plus 0.5x plus 4, where x represents the quality of the fingerprint on a scale of 0 to 10. In part A, we want to find the rate of change in success rate at x equals 8. In part B, we want to find the equation of the tangent line at x equals 8. Well, for part A, all we're doing is finding the derivative and plugging in x equals 8. So let's find the derivative. We have f prime of x is equal to, now we have 0.9x squared, and when we take the derivative here, the 2 will come out in front. Looks like that gives us 1.8x, and from 0.5x, we just get 0.5. Because 4 is a constant, we get 0. So f prime of x is equal to 1.8x plus 0.5. And from here, we can see that f prime of 8 is 1.8 times 8 plus 0.5, and that just gives us 14.9. All right, now let's take a look at part B. And here we want to find the equation of the tangent line at x equals 8. Now let's remember that to find the equation of a line, there are two things that we need. We need a point, and I'm going to call that x1, y1, and we need the slope, which we'll call m. Now if we have these two things, the equation of the tangent line is given by y equals m times x minus x1 plus y1. And that's called the point-slope formula. So let's think about what we have here. We know that the slope of the tangent line at x equals 8 is 14.9, so this part is given to us. We also know that the x-coordinate of the point we're interested in is 8, So we at least have the x value here, and I can find the y value by plugging 8 back into the original function. Now when we throw this in the calculator, we find this y value to be 65.6. So it looks like the equation of the tangent line here will be y equals elm, which is 14.9, times x minus x1, so that will be x minus 8, plus y1, which is 65.6. So y is equal to 14.9x minus, we find this to be 119.2 plus 65.6. Looks like we get the equation of the tangent line to be 14.9x minus 53.6. In this module, we explored basic derivative rules. To broaden our capacity to find derivatives for a wider range of functions, we will introduce additional rules in the upcoming modules, so stay tuned.